Hi guys, welcome to the machine learning playlist, and in this video we're going to learn multi-variate linear regression. Now, as opposed to simple linear regression, you can make it out from the name. It consists of multiple variables on which a single dependent variable can relate to. Now, in case of simple linear regression, we only had this one feature, that is, the price of a house was dependent on the number of rooms, but that's not the case in real life, right? The price of a house can depend on a lot of other features like the area, if it has a garage or not, the distance from a particular landmark, and many other features. So for simplicity, I'm taking just four examples here and just the four independent variables, which we also call as features. So I'm going to write this down for you. Features, right? So we can make out from this data set that our dependent variable y must be dependent on these variables in the form of the equation such that y equals to theta naught x naught plus theta 1 x1 plus theta 2 x2 and so on until theta n x of n. Now, since we don't have x naught, we can actually replace this with 1. So we want this theta naught to be a constant parameter which is not related to any x. So yeah, we can keep theta naught. We can keep theta naught independent of x, and x naught will be 1. So from this equation, we can form a hypothesis, and the hypothesis goes like h. So small h equals to theta naught again plus theta 1 x1 plus theta 2 x2 till theta n x of n. Now this h is only for one single example, that is I. So I'm going to put I on top of all x's here, right? Now, as you can see from this data set, can we represent this data set in the form of a matrix? Now, if we represent this in the form of a matrix, it will be much easier for us to represent this hypothesis equation. So I can say the feature matrix, the 16 numbers that we have here, we can represent the feature matrix in the form of a variable like x, which is the shape of. So there are 4 rows, 4 columns. So it will be the rows are the number of examples, right? So x of m cross, and features, they are the number of features. Features are the number of columns. So it would be, so features are the number of columns, but again we have x0, which is 1. So it would actually be, so if we extend this to x of n, it would be m cross n plus 1. And y, on the other hand, y would be a column vector. So y would be a column vector with the dimensions of m cross 1, as simple as that. And theta would be a single row vector, that's theta naught, theta 1, theta 2 until theta n. So theta can be represented, so dimensions of theta would be 1 cross n plus 1, right? So we can represent this hypothesis equation in the form of a linear algebra matrix equation such that h of m cross 1 would be equal to x of m cross n plus 1 multiplied with theta. So theta would have a dimension of 1 cross n plus 1 transpose. Now since we're adding the transpose, let's say delta equals to theta transpose, alright? Let's write it down here. Delta equals to theta transpose. Now since theta transpose is 1 cross n plus 1, so delta would be n plus 1 cross 1. So now you can actually write this as delta of n plus 1 cross 1. Now you can see this multiplication conforms to the rules of matrix multiplication. So now that we have our hypothesis, we can go on to find out the cost function and the gradient equation. So as we know from simple linear regression, the cost function would be j of theta equals to 1 by 2m summation of I equals to 1 to m, that is m is the number of examples, h of I minus y of I square. Now h of y and y of y will represent only one single example, but if we want to sort of represent them in the form of matrix, we can actually write capital H and capital Y. But again, in the end, we'll have to take the average of all of them. So this is basically we're first taking the error. So you can also write this as the error square, right? So this is the error, this is the square. You're squaring the error, and then you're taking the average of all the error across the entire training set. Right? So this is an equation for the cost function. Then we will find out the gradient, that is del of j theta divided by with respect to del of theta j. So we need to find the gradient of j with respect to different theta. So that would be equal to 1 by m again, summation of I equals to 1 to m, again h of I minus y of I multiplied with x of I. Now again, there will be a j here, obviously. Yeah, so x of j superscript I represents the input with respect to theta j with I number example in the training set. So this is our gradient function. And again, for updating, we will have theta j new equals to theta j old minus our learning factor alpha derivative of j theta with respect to theta j. So here we have found out the three equations, four equations in fact. First we had our hypothesis, then we had our cost function, then our gradient equation, and then this is the updating function. I hope you can sort of relate multivariate linear regression with simple linear regression. There is not much difference. The only fact is that we have to introduce this extra parameter j because we are using multiple features here. So yeah, you can get the intuition of this from simple linear regression. It's not much different that's going on here. So I guess in the next video we will go through some parameters that we can use to simplify or to make multivariate linear regression work much better or much faster than it's supposed to be. That will be all for this video. Thank you and have a nice day.